Hello, my name is James Pearce-Higgins and I'm Director of Science for the BTO, the British Trust for Ornithology. And I'm going to be talking to you today about the impacts of climate change on terrestrial ecosystems. Before I start, I just want to draw your attention to these three documents at the bottom of the screen. So the UK Climate Change Risk Assessment, Chapter 3, the Biodiversity Climate Change Impacts LWET report cards, and the 2017 issue of the State of UK Birds, which has a particular climate change focus. If you want to find out more about the impacts and projected future impacts of climate change on terrestrial ecosystems, then do have a look at these. And the first thing I want to say about impacts, which I'll start off with, is that those impacts are pretty widespread. If we look at habitats, and this is an infographic from the LWET report card, you can see that there's evidence of impacts of climate change right across the landscape, from impacts changing the composition of montane vegetation on tops of mountains, right down to saline intrusion and coastal wetland habitats from storm surges and rising sea levels, and everywhere in between. Those impacts are similarly widespread across species populations. So if we look at changes in the abundance of 5 species groups, so aphids, butterflies, moths, mammals, and birds, as tracked by various long-term citizen science monitoring schemes, you can see that there's strong evidence of changes, interannual changes, particularly with the invertebrates, as shown by black, and long-term trends as well. And we can model these as a function of climate and sort of long-term changes in relation to time. And if we do that for lots of different species and average out those trends and compare that with the observed trends, that gives us the black dotted line. So there's pretty good fits there for those different species groups. But if we then pull out the trend that's consistent with what we'd expect from climate change in red, you can see there's definitely a climate change component in terms of those trends. So particularly for aphids, where about 40 to 50% of the observed increase in aphids through time is consistent with what our models would expect from climate change impacts, and from in relation to moths, where about 50% of the observed decline in moths is consistent with negative impacts of warmer, wetter winters, based on as our models would describe. Now, even for the groups where there's no overall strong impact of climate change on their overall pattern of trend, so for the birds, for example, if we zoom in on that in the top and the left-hand side of the screen here, you can see there's a strong decline across bird species during the 70s and 80s as a result, particularly of agricultural intensification. But the fact that we don't see that being driven by climate change in red doesn't mean that these species aren't affected by climate change. And actually, in a more recent analysis, we show that about 1/3 of our bird species show evidence of changes in populations from one year to the next being affected by temperature and rainfall variables. And the long-term impacts of those are illustrated by the predictions in relation to grey partridge on the top right and long-tailed tit bottom right, where we can see that observed trends in black match pretty well what our models would predict, again as a function of weather variables through time and long-term trends, as shown in red. And if we detrend the climate data as a surrogate for removing the impacts of climate change, we can see that both species are actually more abundant now than they would have been in the absence of warming. So warmer summers have benefited grey partridges, even though their populations have crashed nationally as a result of agricultural intensification. And the increase in long-tailed tits is largely as a result of warmer winters through time, as you can see in the bottom. As well as impacts on populations, we also see strong evidence for changes in species distributions across the country. So to illustrate the sort of data I'm talking about, the map on the left shows the distribution of the small skipper during the 60s and early 70s, so found only as far roughly as Yorkshire. But if we scroll through time, up through the 80s and early 90s to the early 2000s, where it's pretty much on the Scottish border, we can see there's evidence of a strong 120 or so kilometre advance northwards. This has been repeated for many species in all of these different species groups, as shown by the bar graphs. And you can see in the vast majority, there's evidence of that northward range expansion, as shown by the bars above the line. So particularly significant for flying invertebrates like hoverflies, butterflies, dragonflies, and so forth. So there's really strong evidence for climate change affecting many species groups and many habitats. And of course, the magnitude of future climate change is likely to be even more dramatic. And we can get a handle of that using modelling. So here we show a map of curlew densities modelled from breeding bird survey data on the left. And then by modelling that as a function of climate and land cover, we then assess what the future changes in the distribution and abundance of curlew will be in response to a medium climate change scenario, so of about 3 to 3.5 degrees warming globally by the 2050s and 2080s. And compare that for a low emission scenario in that graph on the bottom right in blue, and a high emission scenario of over 4.5 degrees warming in red. So this is a species which is projected to decline significantly in response to climate change. We do this for a wide range of our bird species, and actually many of our bird species are projected to increase in abundance in response to climate change. And that's for the reasons that I outlined earlier in terms of many of our birds, particularly resident species, do better when the winters are warmer, and actually many species benefit from warmer temperatures during the breeding season. But if you focus on the red list species on the right-hand side, species of conservation concern, those are the ones that seem to be most vulnerable to negative impacts of climate change. And you can see that mapped out here with the generally positive impact of many bird species everywhere increasing, but those red list species particularly vulnerable to decline in the south and the east. And the severity of those declines are linked to the magnitude of climate change. So these maps on the right, if you go from the low emission scenario in the top to the high emission scenario at the bottom, and 2050s on the left to the 2080s on the right, you can see with increasing magnitude of climate change, there's increasing severity of decline with these red list species. And we can undertake these sorts of modelling approaches for a wide range of taxa, and you can see there's strong variation between those taxa. So southerly distributed groups like the ants, bees and wasps, the Hymenoptera, many of which are associated with warmth, are actually projected to benefit and do potentially expand their ranges in response to warming, whereas some other taxa like bryophytes, mosses and so forth, or some of our vascular plants show more of a mixed picture. And if we break these down by habitats, particularly the species and the species groups which are associated with our uplands and therefore cold associated, which are the ones that are most vulnerable to climate change, shown here in the middle, where about 3/4 of upland species are thought to be at risk from negative impacts of climate change. So now just finally, I want to go from thinking about the impacts of climate change to what that means in terms of adaptation. Obviously, there'll be a lot more on adaptation later on in this conference. So this is the golden plover, one of the vulnerable upland species that I was just been talking to you about, and it's widespread on peatlands in the UK, where it's pretty much at the southern edge of its global range. The growth and survival of those cute golden plover chicks, as you can see in the bottom right, is very dependent on the availability of invertebrates, and particularly crane flies. And the abundance of those crane flies, as you can see top right, is negatively correlated with temperature. These insects have an annual life cycle, and if you get a hot summer, then the abundance of their larvae, the survival of their larvae, is severely compromised as the peat dries out. And that negative effect of temperature translates through to a negative effect on golden plover populations the following year, as you can see in the graph on the bottom left. So a hot summer reduces crane flies the following year, which reduces the survival of golden plover chicks, which means that the golden plover population then declines the next year. And if you take that trend forward through time, we would expect that that would lead to a population decline of this population in the Peak District to extinction by the end of the century, as shown by these red lines, compared to a stable climate, as shown in blue. So what does that mean in terms of the management of these sites? Well, we know, as I said, that crane flies abundance is linked to soil moisture, and many of our upland areas have historically been drained to try and improve their productivity. These drains are now being blocked by conservation organisations to try and restore peatland habitats to their former glory. And as you can see in that middle graph, if you block those drainage ditches, that results in a significant increase in soil moisture, both next to the drainage ditches, near, or even extending 10 metres away far and beyond. And those block drainage ditches are associated with a much higher abundance of crane fly abundance, as you can see in that far right graph. So restoring these habitats by blocking these drainage ditches increases the availability of and the abundance of crane flies. And some modelling work that we've done on this golden plover population in the Peak District suggests that undertaking this adaptation management by improving the quality of the peatland and some other measures would expect this population to cope with about 2.5 degrees warming, and therefore be much more resilient to the impacts of climate change than it otherwise would be, as you can see by these blue lines on the right, bottom right. So just to summarize, I hope I've shown you that the impacts of climate change are widespread and the projected impacts are likely to be even greater. But it's worth bearing in mind, particularly from a UK context, that those impacts are not always negative, and many species may well do better in response to climate change. Understanding why and the mechanisms underpinning those species responses to climate change and system responses as well can help inform adaptation. And it's worth making the case that healthy ecosystems will also deliver many good ecosystem services for people as well. But all of this understanding is dependent on good terrestrial surveillance and monitoring data, such as supported by JNCC and its work in collaboration and partnership with many NGOs like ourselves at the BTO. That long-term data gives us the ability to monitor the long-term impacts of climate change and then potentially the effectiveness of our adaptation responses. Thank you very much.